What if the universe just sent us a messenger and we're only now realizing it brought a message we don't want to hear? What if an object we thought we understood, categorized, measured, and dismissed suddenly defied every expectation we had about how celestial visitors should behave? What if something from beyond our solar system, something that traveled through the cosmic void for potentially millions of years, woke up just as it was supposed to be falling silent? Tonight, we venture into territory where the comfortable boundaries of astronomical certainty begin to blur, where an interstellar interloper designated 3I Atlas has done something that sends a chill down the spines of astronomers worldwide. It became active again, after perihelion, after it should have been settling down, cooling off, returning to the dormant state befitting a cosmic wanderer leaving our neighborhood. The object known as 3I Atlas, the third confirmed interstellar object to visit our solar system, has been under intensive observation since its discovery. Scientists tracked it as it approached the Sun, watched it brighten predictably as solar radiation heated its surface, documented its expected outgassing as volatile materials sublimated into space. Everything was going according to the celestial playbook written by centuries of comet observation. And then, as it swung around our star and began its journey back into the darkness between the stars, something changed. The brightening shouldn't be happening. The renewed activity defies the standard model. According to everything we know about comets, about icy bodies heated by solar radiation, about the physics of sublimation and outgassing, 3I Atlas should be dimming, quieting, returning to its frozen slumber. Instead, it's flaring, it's active, it's doing something that makes astronomers check their instruments, rerun their calculations, and wonder if perhaps this visitor from another star system plays by different rules than the objects born in our own cosmic backyard. Is this simply an unexpected quirk of exotic chemistry? Some volatile compound we've never encountered before, trapped in ice from an alien solar system, now releasing in a way that surprises us? Or is this something more? Could this be evidence that 3I Atlas isn't quite what it appears, that its renewed activity after perihelion represents not a physical phenomenon, but something else entirely? What if the worst-case scenario isn't about collision or contamination, but about recognition? The night sky has always been humanity's first mystery, the canvas upon which we projected our deepest fears and greatest hopes. For thousands of years, we looked up and saw omens, portents, signs and wonders. We moved past that, we thought. We became rational, scientific, capable of distinguishing between superstition and fact. But what happens when an object from beyond our stellar neighborhood acts in ways we cannot easily explain? What happens when the facts themselves become unsettling? This is not a story about panic or unfounded fear. This is a story about scientific observation colliding with the unknown, about the moment when our models fail to predict, when our understanding reaches its limits, and the cosmos reminds us how much we still have to learn. This is about 3I Atlas, an interstellar object that has become active again after perihelion, and what that might mean for our understanding of the universe, our place in it, and the profound question of whether we're truly alone. The data is real, the renewed activity is confirmed, the implications stretch from the purely scientific to the deeply philosophical, from the technical details of volatile sublimation to questions about intelligence, intention, and the nature of what we classify as natural versus artificial. Tonight we explore all of it, the facts, the speculation, the hope, and yes, the fear. Because 3I Atlas has given us a gift, uncertainty. And in that uncertainty lies the opportunity to expand our understanding of what's possible in this vast, strange universe we call home. Before we dive deeper into this absolutely fascinating and unprecedented story, if you're intrigued by interstellar mysteries, cosmic visitors from beyond our solar system, and the cutting edge of astronomical observation that's rewriting our understanding of what's out there, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is, where you're watching from, and where you're located. I genuinely love seeing our global community come together to explore these cosmic questions that unite us all under the same mysterious sky. And if you appreciate the deep research that goes into these explorations, the careful balance between scientific rigor and genuine wonder alike really helps the channel grow and reach more people who are hungry for this kind of thoughtful investigation into the unknowns that surround us. Your engagement tells YouTube's algorithm that there's an audience for substantive, nuanced discussions of cosmic mysteries, and that matters more than you might think in keeping this kind of content visible. Now let's continue our journey into the strange case of 3I Atlas and its unexpected awakening. Let's address the immediate concern first, the question that always surfaces when we discuss objects from interstellar space. Is 3I Atlas dangerous? Does its renewed activity after perihelion represent any kind of threat to Earth, to our satellites, to the delicate technological infrastructure we've built in near-Earth space? The answer, according to every credible astronomer and space agency monitoring this object, is an unequivocal number 3I Atlas poses zero collision risk to Earth. Its trajectory has been calculated with extreme precision, tracked by observatories across the globe, and refined through weeks of continuous monitoring. The object's path takes it nowhere near our planet's orbital corridor. It passed through the inner solar system, swung around the Sun at its perihelion point, and is now on an outbound trajectory that will carry it back into interstellar space. Earth is not in its path. We are safe from any direct physical interaction. NASA, the European Space Agency, and observatories worldwide have issued consistent statements on this point. The trajectory is hyperbolic, meaning this object came from interstellar space and will return to interstellar space. It is not bound by our Sun's gravity. It's not going to orbit back around for another pass. This is a one-time visit, a cosmic flyby, and the geometry of its path means we can observe it, study it, and marvel at it without any concern for collision. The renewed activity, the unexpected brightening and outgassing that has captured astronomers' attention, does not change this fundamental fact. Whether 3I Atlas is releasing water vapor, carbon dioxide, nitrogen ice, or any exotic volatile compound, whether it's producing a coma and tail or fragmenting or doing something we've never seen before, none of these possibilities alter its trajectory. The laws of orbital mechanics are clear, predictable, and uncompromising. 3I Atlas is leaving our solar system, and nothing about its current activity suggests otherwise. Furthermore, there is no radiation risk. The object is not emitting dangerous particles or electromagnetic radiation that could affect Earth or its inhabitants. It's not trailing a debris field that threatens satellites. It's simply an icy body, or rocky body, with volatile compounds that is sublimating material as it responds to solar heating. This is normal behavior for comets, even if the timing is unusual. The material being released poses no threat to our planet from this distance. Space agencies have protocols for assessing threats from near-Earth objects. These protocols involve calculating potential impact trajectories, assessing the size and composition of threatening objects, and determining the likelihood of collision events that could cause regional or global damage. 3I Atlas triggers none of these concerns. It fails every criterion for being classified as a potentially hazardous object. It is too far away, on the wrong trajectory, and lacks any characteristic that would make it dangerous. This bears repeating because sensationalism often clouds discussions of interstellar objects. 3I Atlas is not a threat to Earth. The science is clear. The mathematics is unambiguous. The observations confirm it. Any discussion of this object's unusual behavior must start from this foundation of safety, this bedrock certainty that whatever mysteries 3I Atlas presents, physical danger to our planet is not among them. That said, and this is where our journey takes a more intriguing turn, the absence of physical threat does not mean the absence of significance. The renewed activity after perihelion is scientifically puzzling. It challenges our models of how cometary bodies should behave. It raises questions about the composition, origin, and nature of objects that form around other stars. And in those questions, in that scientific uncertainty, lies something far more interesting than danger: the opportunity to expand our understanding of the cosmos. Despite these reassuring facts about safety, despite the clear evidence that 3I Atlas poses no collision risk, what shadows might lurk in the implications of its behavior? What does it mean when a visitor from another star system defies our expectations? And if this object is doing something we don't fully understand, what else might we have missed about the nature of interstellar space, the objects that travel through it, and the possibility that the universe is stranger and more complex than our models suggest? To understand the significance of 3I Atlas and its unexpected reactivation, we need to grasp the sheer scale of what we're discussing. The numbers associated with this object stagger the imagination and put into stark relief just how extraordinary interstellar visits truly are. 3I Atlas was discovered on April 14, 2024, by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to detect potentially hazardous asteroids. The 3I designation marks it as only the third confirmed interstellar object observed passing through our solar system. The first was 1I Oumuamua in 2017, the second was 2I Borisov in 2019, and now 3I Atlas has joined this exclusive list. The object's speed tells us immediately that it's not from our neighborhood. 3I Atlas is traveling at approximately 30 to 35 kilometers per second relative to the Sun. That's roughly 67,000 to 78,000 miles per hour. To put that in perspective, the fastest human-made object, the Parker Solar Probe, at its maximum velocity reaches about 120 kilometers per second, but only achieves that speed through carefully planned gravitational assists from the Sun itself. 3I Atlas is maintaining its tremendous velocity naturally, carrying the momentum from its origin star system. This velocity is the signature of an interstellar origin. Objects born in our solar system and bound to the Sun's gravity move at speeds determined by their orbital parameters, typically ranging from a few kilometers per second for distant trans-Neptunian objects to perhaps 50 kilometers per second for sun-grazing comets at perihelion, but they're bound, they're enclosed orbits. 3I Atlas's trajectory is hyperbolic, open-ended, meaning it has enough velocity to escape the Sun's gravitational well entirely. It came from somewhere else and it's returning to the interstellar void. The distance it has traveled is almost incomprehensible. The nearest star to our Sun is Proxima Centauri, about 4.4 light-years away. That's approximately 40 trillion kilometers, or 25 trillion miles. If 3I Atlas came from even the nearest stellar neighborhood, and we don't know its exact origin, it has been traveling through the void of space for potentially hundreds of thousands or even millions of years. Think about that. This object may have been in transit before humanity evolved, before our species even existed, journeying through the darkness between stars in absolute silence and cold. The size of 3I Atlas remains somewhat uncertain, as is often the case with newly discovered distant objects. Initial estimates suggest it may be between a few hundred meters to perhaps a kilometer in diameter, roughly the size of a large mountain or a small city. This puts it in the same class as 2I Borisov, which had a nucleus estimated at around 500 meters, but significantly smaller than some of the wild early estimates for Oumuamua. Determining exact size is challenging because what we observe is not just the solid nucleus, but the brightness of reflected sunlight and any outgassing activity that creates a coma of gas and dust around the object. The perihelion distance, the closest approach to the Sun, occurred in late 2024 or early 2025, exact date dependent on refined orbital calculations. This is the point where 3I Atlas received maximum solar heating, where temperatures on its surface would have risen dramatically, where any volatile materials, water ice, carbon dioxide, nitrogen, methane, would have been most susceptible to sublimation. Standard models predict that cometary activity should peak around perihelion or shortly after, then decline steadily as the object moves away from the Sun and temperatures drop. The fact that 3I Atlas became active again well after perihelion violates this expectation. But what if these numbers hide something more? What if the renewed activity after perihelion isn't about exotic chemistry or unusual composition, but about something responding to perihelion passage itself? What if an object traveling through interstellar space for hundreds of thousands of years, suddenly exposed to the intense radiation environment of a close solar approach, underwent some kind of transformation we don't understand? The temperature differentials involved are extreme. In interstellar space, 3I Atlas would have been at temperatures approaching absolute zero, perhaps 10 to 20 Kelvin, just a few degrees above the cosmic microwave background radiation. At perihelion, depending on its exact distance from the Sun, surface temperatures could have spiked to several hundred Kelvin or more. That's a temperature swing of several hundred degrees, a thermal shock that could potentially fracture ice, release trapped volatiles from deep within the object's interior, or trigger delayed sublimation of materials that heat slowly. Or, and this is where speculation begins to creep in, what if something about that perihelion passage activated something? What if an object that had been dormant, frozen, essentially dead for eons, suddenly experienced an event that triggered a response? Not a chemical or physical response, but something else. We must be careful here. The data shows renewed activity. The data does not show anything artificial or intentional, but the human mind, faced with the unexpected, begins to wonder. And in that wondering lies both the danger of unfounded speculation and the potential for breakthrough thinking that challenges our assumptions. What makes 3I Atlas truly extraordinary is not its interstellar origin. We've now confirmed 3 such objects, suggesting that interstellar visitors may be more common than we previously thought. What makes it extraordinary is its behavior. The renewed activity after perihelion is an anomaly, a deviation from expected patterns that has astronomers reviewing their data and questioning their models. Standard cometary behavior follows a predictable pattern. As a comet approaches the Sun, increasing solar radiation heats its surface. Volatile materials, primarily water ice, but also frozen carbon dioxide, carbon monoxide, nitrogen, methane, and other compounds begin to sublimate, transitioning directly from solid to gas without becoming liquid. This outgassing creates pressure that lifts dust particles off the nucleus, forming the characteristic coma, a cloud of gas and dust around the nucleus, and, if the activity is strong enough, a tail that points away from the Sun due to solar wind and radiation pressure. Activity typically peaks at or shortly after perihelion, when temperatures are highest. As the comet recedes from the Sun, temperatures drop, sublimation decreases, and the comet turns off, returning to dormancy. This pattern has been observed in countless comets over centuries of astronomical observation. It's so reliable that astronomers can predict brightness curves and activity levels based primarily on distance from the Sun and estimated composition. 2I Borisov, the previous interstellar comet, followed this pattern beautifully. It showed increasing activity as it approached the Sun, peaked around perihelion, and then faded as it departed. It behaved exactly like a comet should behave, providing reassurance that objects formed around other stars follow the same physical laws as objects born in our solar system. The chemistry might differ slightly, the composition might show exotic ratios of volatiles, but the fundamental physics remained constant. 3I Atlas is different. Initial observations showed expected behavior, brightening as it approached the Sun, developing a coma, exhibiting outgassing consistent with volatile sublimation. And then, well past perihelion, as it moved outward and should have been fading, it brightened again. It became active again. Telescopes detected renewed outgassing, increased brightness, behavior that suggests something triggered a fresh release of material after the object had already passed its closest approach to the Sun. Several scientific explanations have been proposed. The leading hypothesis involves delayed sublimation of volatiles from beneath the surface. If Atlas has a thick outer crust, perhaps a layer of dust, and refractory material that insulates the interior, heat from perihelion passage might have taken time to conduct inward. Eventually, that heat could reach buried pockets of highly volatile materials, causing them to suddenly sublimate and burst through the surface in a delayed eruption. This would be unusual but not unprecedented. Some comets in our solar system have shown similar delayed outbursts. Another possibility involves the rotation of the object. If 3I Atlas is rotating with a particular orientation, different surface regions would be exposed to maximum solar heating at different times. A delayed brightening could occur if a particularly volatile-rich region of the surface only received maximum heating after the formal perihelion point due to the geometry of rotation and solar illumination. Fragmentation presents another explanation. If thermal stresses from perihelion cause the object to crack or break apart, fresh interior material would be exposed to sunlight and vacuum for the first time. Interior ice, protected from millions of years of cosmic ray bombardment and interstellar heating, might be particularly rich in volatile compounds. Sudden exposure would cause rapid sublimation and renewed activity. Exotic volatiles offer yet another avenue. Most comets in our solar system formed in the outer reaches of the solar nebula and consist primarily of water ice with smaller amounts of other frozen gases. But 3I Atlas formed around a different star in a possibly different chemical environment. What if it contains significant amounts of carbon monoxide ice, or nitrogen ice, or other compounds with lower sublimation temperatures than water? These materials might remain frozen even at temperatures where water ice sublimates, then suddenly transition to gas as the object moves farther from the Sun and temperatures drop into a different range, a counterintuitive but physically plausible scenario. Each of these explanations is scientifically sound. Each could potentially account for renewed activity after perihelion, and yet the observations remain puzzling because they push at the boundaries of what we typically see. 3I Atlas is not behaving like a normal comet, even acknowledging that comets can be unpredictable and individual objects often show unique characteristics. This chemical and physical signature opens doors to speculation that scientists are generally reluctant to walk through publicly, but which hover at the edges of professional conversations. What if the renewed activity isn't spontaneous? What if it's responsive? What if, and I want to be absolutely clear, this is speculation without evidential support, what if something about perihelion passage triggered not just physical changes but something more complex? Before we venture deeper into speculative territory, we must definitively address the worst-case physical scenario, because this is what most people fear when they hear about unusual behavior from space objects. Could 3I Atlas pose any threat? Could its renewed activity indicate fragmentation that might send dangerous debris toward Earth? Could it explode? Could it release toxic gases or biologically dangerous materials? The answer to all of these questions is no, and the reasons are grounded in precise scientific calculations and observational data. First, the trajectory. 3I Atlas is moving away from the inner solar system on a hyperbolic escape trajectory. Its path has been calculated with extraordinary precision using data from multiple observatories worldwide. The orbit is not circular or elliptical, but parabolic, meaning the object is not bound to our Sun. It came from interstellar space, traveling faster than our sun's escape velocity, swung through the inner system, and is now returning to interstellar space. At no point does this trajectory intersect Earth's orbital path. Current distance calculations place 3I Atlas well beyond Earth's orbit and increasing. Even if the object were to completely fragment, break into thousands of pieces, those pieces would maintain the general trajectory of the parent body. Fragmentation doesn't magically redirect debris onto collision courses with planets. It disperses material along the original trajectory. The debris field would continue outward, away from Earth, posing no collision risk. Second, the composition. All observational evidence suggests 3I Atlas is a cometary body composed primarily of ice and rock, similar to other comets we've observed. The renewed activity involves outgassing of volatile materials, gases and dust particles being released as ice sublimates. These materials disperse into space rapidly, creating no hazard at the distances involved. The gas molecules released by 3I Atlas would need to travel millions of kilometers to reach Earth, by which point they would be so dispersed as to be undetectable, let alone dangerous. There is no realistic scenario in which cometary outgassing from an object millions of kilometers away could affect Earth's atmosphere or biosphere. The quantities involved are minuscule compared to atmospheric volumes. The materials released are common compounds, water vapor, carbon dioxide, simple organics, that exist naturally in space and in Earth's atmosphere. There is no exotic toxin, no biological contamination scenario that makes sense given the physics involved. Third, the energy considerations. Some might wonder if the renewed activity indicates that 3I Atlas could explode, releasing energy that might somehow affect Earth. Cometary outbursts can be dramatic from an observational standpoint. Sudden brightness increases, expanding comas, but they involve relatively small amounts of energy. A comet nucleus is not a bomb. It doesn't contain compressed explosives or nuclear materials. The explosion of outgassing is simply rapid sublimation, gas expanding because it's transitioning from solid to gaseous state and escaping the weak gravity of the small nucleus. Even if 3I Atlas were to completely disintegrate, which is not happening based on current observations, the energy release would be trivial on cosmic scales and completely inconsequential at Earth's distance. We're talking about a rocky, icy body a few hundred meters to perhaps a kilometer in diameter. Complete disintegration would release less energy than a modest volcanic eruption, and that energy would be dispersed into empty space, not directed at any particular target. Fourth, the electromagnetic considerations. There's no evidence that 3I Atlas is emitting any unusual electromagnetic radiation. It's not a radio source, not an X-ray source, not emitting gamma rays or dangerous ultraviolet radiation. It's simply reflecting sunlight and emitting the thermal radiation characteristic of an object at its temperature. This poses absolutely no threat to Earth's electromagnetic environment, our satellites, or our technology. Space agencies have specific criteria for classifying objects as potentially hazardous. An object must meet two conditions. It must approach within 0.05 astronomical units, about 7.5 million kilometers, of Earth's orbit, and it must be larger than approximately 140 meters in diameter. 3I Atlas fails the first criterion spectacularly. It never came close to Earth's orbital corridor. Therefore, regardless of its size, it is not classified as potentially hazardous. This bears repeating because clarity is essential. The renewed activity of 3I Atlas, however unusual or scientifically interesting, does not present any physical threat to Earth. The object is too far away, on the wrong trajectory, and lacks any mechanism by which it could harm our planet. Every reputable astronomer and space agency monitoring this object agrees on this point. The science is unambiguous. But, and this is where our exploration takes a more philosophical turn, what if the real worst case has nothing to do with physical danger? What if the implications of an interstellar object behaving in unexpected ways reach into territories far more unsettling than collision or contamination? What if the worst case isn't about what 3i Atlas might do to us, but about what it might reveal about the universe and our place in it? Let's venture into speculative territory. What follows is not established fact, not supported by definitive evidence, but rather an exploration of possibilities that exist at the intersection of physics, astronomy, and our growing understanding that the universe might be far stranger than we imagined. This is the realm of what if, and I want to be absolutely clear about that distinction. What if 3i Atlas isn't simply a comet? What if its renewed activity after perihelion isn't a quirk of exotic chemistry or delayed thermal response, but something more intentional? What if, and this is the speculation that keeps some astronomers awake at night, though few would say it publicly, what if 3i Atlas is a probe? The probe hypothesis for interstellar objects isn't new. It gained prominence with Oumuamua, the first confirmed interstellar object, which exhibited several characteristics that puzzled scientists. Oumuamua showed non-gravitational acceleration. It deviated slightly from the trajectory predicted by gravity alone, suggesting some kind of outgassing or other force was acting on it. Yet no outgassing was observed, no coma, no tail, no visible evidence of the volatile sublimation that typically causes such acceleration in comets. Dr. Avi Loeb, chair of Harvard's astronomy department, proposed that Oumuamua could be a light sail, a thin, reflective sheet designed to be pushed by starlight, a form of propulsion proposed for interstellar travel. This hypothesis was controversial and remains unproven, but it highlighted an important question. How would we recognize an artificial object of extraterrestrial origin if one entered our solar system? The question is not absurd. We know that technological civilizations are possible because we exist as an example. If other technological civilizations exist in our galaxy, and the sheer number of potentially habitable exoplanets discovered in recent years suggests this is plausible. Some of them might be far more advanced than us. They might have developed technologies we can't yet imagine. And one of the most logical things an advanced civilization might do is send probes to explore other star systems. Consider our own trajectory. We've sent Voyager 1 and 2 out of the solar system. We've dispatched New Horizons past Pluto into the Kuiper Belt. We're actively designing concepts for interstellar probes that could reach nearby stars within a human lifetime using proposed technologies like nuclear pulse propulsion or laser-pushed light sails. If we're contemplating such missions with our current technology, what might civilizations with millions of years more development have already accomplished? A truly advanced civilization might seed the galaxy with probes, self-replicating or not, designed to visit star systems and gather data. These probes wouldn't need to announce themselves with radio signals or obvious technological signatures. They might be designed to observe passively, to remain unnoticed, to blend in with natural objects while collecting information about the star systems they visit. Now apply this reasoning to 3i Atlas. It approaches our solar system from interstellar space. It passes through the inner system, receiving maximum exposure to our Sun's radiation at perihelion, an event that would provide tremendous data about our star's properties, our solar wind environment, the electromagnetic characteristics of our heliosphere, and then after perihelion, it becomes active, it releases material, it does something unexpected. What if that activity isn't random? What if perihelion passage was the trigger for some kind of data transmission or observation protocol? What if 3i Atlas is now broadcasting information back to its point of origin, using outgassing as either a communication method or as part of a propulsion system designed to adjust its trajectory for the next phase of its mission? This sounds like science fiction, and it might be, but let's examine what such a probe might look like. It wouldn't be a gleaming spacecraft with visible technology. Interstellar travel times are so long that any probe would need to be designed for extreme durability. Covering the technological core with ice and rock would provide natural shielding from cosmic rays and micrometeorite impacts. Such a probe would, for all observational purposes, look exactly like a comet or asteroid, until it did something that comets and asteroids don't do. Renewed activity after perihelion in this speculative framework could be exactly such a signature. A passive, ice-covered probe would naturally accumulate volatiles on its surface during millions of years in the interstellar medium. As it approached a star, that ice would sublime naturally, making the object appear cometary. But once past perihelion, once the mission-critical data collection was complete, the probe might activate systems that produce additional outgassing, perhaps using stored volatiles, perhaps through some form of propulsion we don't understand. The implications of this scenario are staggering. If 3I Atlas were an extraterrestrial probe, it would mean we're not alone in the universe. It would mean another civilization exists or existed, reached a level of technology sufficient for interstellar exploration, and we are subjects of their observation. It would mean that Earth, our Sun, our solar system, have been catalogued, studied, measured, and reported back to some distant intelligence. What would such a discovery mean for humanity? How would it change our understanding of our cosmic significance? If an advanced civilization has visited our system, why haven't they made contact? Are we considered too primitive, uninteresting, dangerous? Or is the probe autonomous, following programming from a civilization that might no longer exist, a ghost messenger from a dead sender? The social and philosophical implications ripple outward. Religions would need to reconcile the existence of other intelligences in the universe. Our scientific frameworks would need to expand to include the study of xenotechnology. Our political systems would face unprecedented challenges in deciding how to respond, what information to share with the public, whether to attempt communication. But, and this is absolutely critical, we have no evidence that 3I Atlas is anything other than a natural object. The probe hypothesis is speculation, an extreme interpretation of ambiguous data. Renewed activity after perihelion can be explained by conventional physics. The more exotic the claim, the stronger the evidence required, and currently, that extraordinary evidence does not exist, yet the possibility lingers. Every time an interstellar object shows unexpected behavior, the question resurfaces. How would we know? What would definitive proof look like? And if we did find such proof, would we even recognize it? The speculation about 3I Atlas as a potential probe connects to one of the most profound questions in astronomy and philosophy. Where is everybody? This question, formalized as the Fermi paradox, highlights the stark contradiction between the apparent high probability of extraterrestrial civilizations and the complete absence of evidence for them. Our galaxy contains an estimated 200 to 400 billion stars. Recent exoplanet surveys suggest that rocky planets in habitable zones around their stars are common, potentially billions of such worlds in our galaxy alone. Life emerged on Earth relatively quickly in geological terms, suggesting that the formation of life might be a natural consequence of suitable conditions. And yet we see no evidence of other civilizations, no radio signals, no megastructures visible in telescope data, no obvious signs of galaxy-spanning civilizations that millions or billions of years of development should produce. One proposed solution to this paradox is the concept of the Great Filter, some evolutionary step or challenge that is extremely difficult or impossible to pass. The filter could lie behind us, perhaps the emergence of complex life or intelligence is extraordinarily rare, or ahead of us, perhaps technological civilizations inevitably destroy themselves or face some unsurmountable challenge before achieving interstellar capabilities. The discovery of interstellar objects like 3I Atlas, 2I Borisov, and Oumuamua provides data relevant to this question. If interstellar objects are common, and statistical analyses suggest that trillions of such objects might pass through the outer solar system over geological time, then the raw material for panspermia, or directed panspermia, exists. Life, or at least organic precursors, could potentially spread between star systems on natural objects or be deliberately transported. But the absence of obvious technological artifacts in our observations suggests several possibilities. Either technological civilizations are extremely rare, we're among the first, or they're common but don't engage in the kind of galaxy-spanning exploration we might expect, or they employ technologies and methods we can't yet recognize, or they avoid making themselves obvious for reasons we don't understand. The probe hypothesis for objects like 3I Atlas sits at the intersection of these questions. If some interstellar objects are actually probes, it would suggest technological civilizations exist, but operate in ways that make detection difficult. They're not broadcasting their presence, they're observing quietly. This could indicate a mature galactic civilization that has adopted protocols of non-interference, or it could suggest that overt activity in the galaxy is dangerous, that there are predator civilizations making stealth and silent survival strategies. Alternatively, if all interstellar objects are natural, if 3I Atlas is simply a comet with unusual but explicable characteristics, then we're left with the original paradox. The galaxy should be teeming with life and intelligence given the number of potentially habitable worlds, yet we see nothing definitive. This raises profound questions about humanity's future. If the great filter lies ahead of us, what form might it take? Nuclear war, climate catastrophe, artificial intelligence emergence, biological warfare, technological stagnation? Understanding the filter's location has practical implications for risk assessment and long-term planning. If most civilizations fail to achieve stable interstellar capability, we need to understand why and how to avoid that fate. The study of interstellar objects becomes more than just astronomy, it becomes a form of cosmic archaeology. Each object that passes through our system carries information about its place of origin, chemical composition, isotopic ratios, structural characteristics that hint at the environment where it formed. By studying these cosmic ambassadors, we learn about other star systems, other stellar neighborhoods, the diversity of planetary formation processes across the galaxy. And if any of these objects are artificial, they represent something even more valuable, proof that intelligence can survive long enough to reach for the stars, evidence that the filter, whatever it is, can be passed. They would be beacons of hope as much as subjects of scientific inquiry. Connected intimately to the great filter is the broader Fermi paradox, the puzzle that has haunted astronomers and philosophers since Enrico Fermi asked his famous question during a lunch conversation in 1950, "Where is everybody?" The paradox arises from a seemingly straightforward calculation. Our Sun is a relatively young star, only about 4.6 billion years old. The galaxy itself is over 13 billion years old. There are billions of stars older than our Sun, many with planetary systems that formed billions of years before Earth. If life and intelligence are natural evolutionary outcomes given suitable conditions, there should be civilizations in our galaxy that are millions or even billions of years more advanced than us. What could such civilizations accomplish? Our own technological progress, from the first radio transmissions to landing on the moon, took only about 70 years. Our serious thinking about interstellar travel has been ongoing for merely decades. Extrapolate our rate of progress forward 1,000 years, 10,000 years, 1,000,000 years. The technologies available to civilizations with that much development time should be godlike from our perspective. They should be visible. A civilization capable of interstellar travel could colonize the galaxy in a few million years, even traveling at a small fraction of light speed, a blink of an eye in cosmic time. Their megastructures, their communications, their energy signatures should be obvious in our telescopes. We should see Dyson spheres or swarms capturing stellar energy. We should detect radio transmissions or laser communications. We should see evidence of stellar engineering, planetary terraforming, or other massive projects. Yet we see nothing. The galaxy is silent. This is the Fermi paradox, and it's deeply unsettling. Something about our assumptions must be wrong. Either intelligent life is far rarer than we think, or civilizations destroy themselves before achieving interstellar capability, or they're hiding deliberately, or they exist in forms we can't recognize, or some other explanation we haven't considered. Each interstellar object that passes through our solar system represents a test of these hypotheses. If such objects are common natural phenomena, just ice and rock ejected from other stellar systems, then the galaxy is filled with the building blocks of life and planetary systems, but we remain isolated. If even one such object proves artificial, the paradigm shifts entirely. The renewed activity of 3I Atlas matters in this context because it represents ambiguous data. It's behavior that sits at the boundary between expected and anomalous. If we had clear evidence of artificiality, structured radio signals, geometric forms, materials that couldn't form naturally, the ambiguity would vanish. If the object behaved perfectly predictably according to cometry models, we'd simply catalogue it and move on. Instead, we have something in between, an object doing something unusual but not definitively artificial. This ambiguity is itself informative. It suggests that if probes exist, they're designed to be ambiguous to avoid obvious detection. They blend in, they masquerade as natural objects, or more likely, the universe is complex enough that unusual behavior doesn't require artificial explanations, that our models are incomplete, and natural objects can surprise us in ways we haven't anticipated. The philosophical weight of these questions is immense. Are we alone in experiencing consciousness, in asking these questions, in wondering about our place in the cosmos? Or are we one voice in a chorus, perhaps a very young and naive voice, asking questions that older civilizations have long since answered or moved beyond? If the galaxy is truly empty of other intelligence, then we carry a tremendous responsibility. We might be the universe's way of knowing itself, as Carl Sagan once said. We might be the only consciousness in this vast region of space, the only witnesses to the beauty of stars and galaxies, the only beings capable of understanding the cosmic laws that govern reality. Our survival becomes paramount not just for our own sake, but for the preservation of the only window through which this corner of the universe can observe and understand itself. Alternatively, if others exist but remain hidden or silent, we face different questions. Why the silence? What do they know that we don't? Is there a predator species in the galaxy making noise dangerous? Are we in a cosmic nature preserve, being observed but not contacted under some prime directive of non-interference? Or have advanced civilizations simply moved beyond the need or desire to communicate with emerging species like ourselves? The study of 3I Atlas and other interstellar objects won't definitively answer the Fermi paradox, but each observation adds data. Each unexpected behavior forces us to refine our understanding of what's natural and what requires more exotic explanations. And each time we find that natural explanations suffice, we're learning that the universe is stranger, more diverse, more capable of surprising us than our models predicted. This bears repeating. The renewed activity of 3I Atlas, while unusual, does not constitute evidence of artificial origin, but it does remind us how much we still have to learn about the cosmos and how careful we must be about assuming we understand the full range of natural phenomena. Let's continue our speculative exploration with a thought experiment. If 3I Atlas were proven to be an extraterrestrial probe, and to be absolutely clear, we have no such proof, how would humanity respond? What protocols exist for such a discovery? What would be the institutional, political, and social implications of confirmed contact? even if that contact is one-sided observation. The first challenge would be verification. Extraordinary claims require extraordinary evidence, and the burden of proof would be immense. Any detection of potential artificial origin would need to be confirmed by multiple independent observatories using different instruments and methods. The data would need to rule out all natural explanations. The scientific community would need consensus, or at least strong agreement, before any public announcement. Several international frameworks exist for handling potential detections of extraterrestrial intelligence. The SETI Post-Detection Protocol, established by the International Academy of Astronautics, provides guidelines for responding to confirmed signals from extraterrestrial civilizations. While designed primarily for radio or optical SETI detections, the principles would apply to any verified contact scenario. Key elements of these protocols include immediate verification through independent observation, notification of relevant national authorities, coordination through the International Astronomical Union, public announcement only after confirmation, protection of discovery data and analysis, coordination of any response message, though this is primarily relevant for two-way communication scenarios. In the case of an interstellar object like 3I Atlas proving artificial, the response would be different from detecting a radio signal. The object is physical, moving through our solar system, potentially observable in detail if we could mount a mission to intercept it. This raises fascinating possibilities and challenges. NASA, ESA, and other space agencies have demonstrated the ability to plan and execute rapid response missions. The Hubble Space Telescope can be redirected to observe targets of opportunity. Ground-based observatories can coordinate campaigns, but intercepting an object on a hyperbolic trajectory moving at 30+ kilometers per second relative to the Sun is extraordinarily difficult. By the time we confirmed unusual characteristics and planned a mission, the object would likely be too far away to reach with current propulsion technology. This limitation is itself revealing. If extraterrestrial probes exist and visit our solar system, we currently lack the technological capability to examine them up close unless we detect them early and have spacecraft on standby. This might be by design. Probes that move quickly through star systems minimize the chance of capture or detailed examination by emerging technological civilizations. The political implications of confirmed extraterrestrial artifact detection would be unprecedented. Governments would need to coordinate responses, share information, or decide not to, and manage public communication. The United Nations has committees that deal with outer space affairs, but none specifically designed for this scenario. Ad hoc coordination would be necessary. Different nations might have different priorities. Some might prioritize scientific study, others military assessment, others religious or philosophical implications. The potential for international cooperation or conflict would depend on the specifics of the discovery and the geopolitical climate at the time. Public reaction is difficult to predict. Would such a discovery cause panic? Probably not widespread panic. The object poses no physical threat, and people are generally more resilient than disaster scenarios suggest. But it would cause profound psychological and philosophical disruption. Every religious tradition would need to incorporate this new reality. Every person would need to reconcile their understanding of humanity's place in the universe with the confirmed existence of other intelligence. The scientific community would be energized. Xenoarchaeology would transform from a speculative field to an active discipline. Enormous resources would flow into studying the object, searching for similar objects, and developing technologies to intercept future visitors. SETI would receive renewed funding and attention. The search for biosignatures on exoplanets would intensify, as confirmed intelligence in the galaxy would raise the probability that life is common. Educational institutions would need to update curricula. Philosophy courses would need to address confirmed contact. History courses would mark this as a civilizational turning point. The humanities would grapple with what it means to be human in a universe where we're not the only technological species. Economics would shift in subtle ways. Space technology companies would see increased investment. Materials, science, propulsion research, and AI development would accelerate as humanity sought to understand and potentially replicate the technologies observed. New industries might emerge around the study and exploitation of interstellar object visitation. But all of this assumes proof, and proof is precisely what we don't have. The renewed activity of 3I Atlas is interesting, anomalous, worthy of study, but not proof of artificial origin. What we have is an opportunity to practice our thinking about these scenarios, to refine our protocols, to consider how we would respond if confronted with unambiguous evidence. The very act of thinking through these scenarios is valuable. It reveals our assumptions, our biases, our hopes and fears. It forces us to confront the question of what we would do if we discovered we're not alone, and in that confrontation, we learn something about ourselves. One of the most fraught questions surrounding any potential discovery of extraterrestrial intelligence or artifacts is how to handle information. Should such a discovery be immediately public? Should there be a period of classified assessment? Who decides what the public should know and when? These questions touch on fundamental tensions between transparency and security, between the public's right to know and the potential for misunderstanding or misuse of information. They also reveal different philosophical approaches to the question of contact. The transparency argument goes like this. Any discovery of extraterrestrial intelligence or artifacts is of such profound importance to all humanity that it must be shared immediately and completely. Keeping such information secret would be a form of elite control over knowledge that affects every person on Earth. The discovery would fundamentally alter our understanding of our place in the universe, and every person has a right to participate in that transformation. Moreover, secrecy breeds conspiracy theories and mistrust, undermining the credibility of institutions. Citizen science and amateur astronomy play crucial roles in this transparency framework. Many significant discoveries, including some near-Earth asteroids and cometary outbursts, have been made by amateur astronomers. The global astronomical community is too distributed and too open to allow long-term secrecy about objects visible in telescopes. This practical reality enforces a degree of transparency whether institutions desire it or not. The counter-argument for managed information release emphasizes the need for verification and context. Announcing a potential extraterrestrial artifact before thorough analysis could cause unnecessary alarm or generate false hope. If the initial interpretation proves wrong, if what seemed artificial turns out to have a natural explanation, the retraction could damage public trust in science. Better to verify exhaustively before making any announcement. There's also a security dimension. If an interstellar object did prove artificial, understanding its capabilities and potential purposes would be critical before public disclosure. While 3I Atlas poses no physical threat on its current trajectory, the confirmed existence of extraterrestrial technology would have profound implications for national security, technological development, and geopolitical dynamics. Some might argue that initial assessment should be classified to allow governments time to understand implications before public announcement. However, this security argument is weaker than it might initially appear. The physics and astronomy communities are international and collaborative. Observations of objects like 3I Atlas come from telescopes around the world. Data is shared rapidly through established networks. Any attempt to classify or suppress information would be obvious and would likely fail, succeeding only in generating distrust and conspiracy theories. The historical precedent of scientific openness serves us well here. The discovery of pulsars, the cosmic microwave background, exoplanets, and gravitational waves were all announced after careful verification, but without government censorship. The scientific community has mechanisms for handling extraordinary claims: peer review, replication, consensus building. These mechanisms aren't perfect, but they're robust and have served humanity's quest for knowledge well. In the specific case of 3I Atlas, the information has been public from the beginning. The object's discovery was announced through standard astronomical channels. The unusual renewed activity has been reported in professional papers and discussed in scientific meetings. This openness is appropriate and healthy. It allows the global scientific community to contribute observations and analysis. It enables informed public discussion. It demonstrates that science can handle ambiguous data without jumping to unwarranted conclusions. The balance between skepticism and openness is delicate but navigable. We should be open to extraordinary possibilities while maintaining rigorous standards of evidence. We should share information while providing context and caveats. We should acknowledge what we don't know without succumbing to unfounded speculation. This approach respects both the scientific method and the public's intelligence. It says, here's what we observe. Here are the natural explanations. Here are the more exotic possibilities. Here's what additional observations or analyses would be needed to distinguish between these explanations. Here's the current state of knowledge, acknowledging uncertainty. The citizens of Earth have proven capable of handling complex, ambiguous information. The discovery of thousands of exoplanets hasn't caused panic, despite the increased probability that life exists elsewhere. The detection of organic molecules in interstellar space and on other planets hasn't triggered societal breakdown. People can distinguish between "this is interesting" and raises questions, and this is definitive proof of something extraordinary. In the case of 3I Atlas, the appropriate response is exactly what's happening. Open scientific investigation, publication of findings, honest discussion of uncertainties, and continued observation. This represents the scientific method at its best: curiosity tempered by rigor, openness balanced by careful interpretation. To truly understand the significance, or lack thereof, of 3I Atlas and its unusual behavior, we need to grasp the immense scale of the cosmic arena in which these events unfold. The numbers involved are so large they become almost meaningless, yet they're essential for maintaining perspective. Our Milky Way galaxy contains an estimated 200 to 400 billion stars. Current exoplanet research suggests that virtually every star has at least one planet, and rocky planets in habitable zones are common, perhaps 20-40 billion potentially habitable worlds in our galaxy alone. That's billions of opportunities for life, for evolution, for the emergence of intelligence and technology. But the galaxy is also staggeringly large. The Milky Way is approximately 100,000 light-years in diameter. A light-year is the distance light travels in 1 year at 300,000 kilometers per second, about 9.5 trillion kilometers, or 6 trillion miles. The space between stars is mostly empty, vast beyond human comprehension. The nearest star to our Sun, Proxima Centauri, is 424 light-years away. That's 40 trillion kilometers of essentially empty space. At the velocities typical of interstellar objects like 3I Atlas, 30 to 50 kilometers per second, the journey between stars takes hundreds of thousands or millions of years. 3I Atlas has been traveling through the interstellar void longer than human civilization has existed. Longer than our species has existed. Possibly longer than the genus Homo has existed on Earth. Think about that journey. For hundreds of thousands of years, this object traveled through absolute darkness, absolute cold, absolute silence. Temperatures approaching absolute zero, no light except the distant stars, no sound. Sound requires a medium, and interstellar space is vacuum, no change, no event, no variation in conditions. Just endless, timeless flight through emptiness. Then suddenly a star grows brighter ahead. Over years and decades, that star resolves from a point to a disk, begins to cast measurable light and heat. A solar system materializes, planets, possibly asteroid belts, maybe comets. The temperature rises, ice begins to sublime, the object becomes active, transforming from a frozen rock into something dynamic, shedding gas and dust, reflecting light. in ways that can be detected by instruments on the third planet from this particular star. And on that third planet, beings who have only recently developed the capability to detect such visitors train their telescopes on this cosmic wanderer. They measure its velocity, calculate its trajectory, analyze its spectrum, document its behavior. They wonder about its origin, its composition, its significance. They ask questions about whether it represents a message, a probe, evidence of other intelligence in the vast cosmic ocean. From the perspective of the object, if it could have perspective, Earth is just another minor planet orbiting just another average star in an unremarkable spiral arm of a typical galaxy. There's nothing special about our solar system from a cosmic standpoint. We're not in a particularly dense stellar neighborhood. Our star isn't unusual. Our location in the galaxy isn't notable. We're deep in the provinces, far from the galactic center, where stars cluster densely. This perspective is simultaneously humbling and clarifying. If interstellar objects like 3I Atlas are probes sent by advanced civilizations, they're probably not targeted specifically at us. More likely, they're part of a galaxy-wide exploration network, visiting thousands or millions of star systems over eons, with just one data point, one observation in a catalogue of stellar systems. Statistical analyses suggest that objects ejected from other stellar systems during planetary formation might be extremely common. For every star with planets, the chaotic early period of planetary system formation likely ejected billions of objects into interstellar space. Over the lifetime of the galaxy, the number of such objects could be staggering, trillions or quadrillions of rocks and ice balls wandering between the stars. Most of these objects would never encounter another star. Space is so vast and objects are so small that the probability of an interstellar object actually passing through another stellar system's planetary region is extraordinarily low. Yet with trillions of objects over billions of years, such encounters become inevitable occasionally. The three confirmed interstellar objects we've detected, Oumuamua, 2I Borisov, and now 3I Atlas, represent only what we can see. Our detection capabilities are limited. Objects need to be large enough, close enough, and bright enough for our telescopes to spot them. Smaller objects, or objects that don't pass close to Earth, remain undetected. The actual number of interstellar objects passing through the outer solar system is certainly much higher than what we've confirmed. This realization cuts both ways. On one hand, it suggests that interstellar visitors are common enough that unusual behavior from one object might simply represent natural variation we haven't observed before. On the other hand, if such visits are common, the probability that at least some are artificial probes increases, assuming technological civilizations exist and engage in galactic exploration. Humanity has been broadcasting radio signals for about 100 years. Those signals have now reached stars within a 100 light-year radius, thousands of stars, but a tiny fraction of the galaxy. If any civilization within that bubble has sensitive receivers pointed in our direction, they know we exist. They've detected our television broadcasts, our radar installations, our radio transmissions. They know we're a technological species. But they're under no obligation to respond. A message traveling at light speed would take decades or centuries to reach us. And why would they respond? We're a very young technological civilization, barely capable of leaving our own planet, nowhere near capable of interstellar travel. From the perspective of an advanced civilization, we're infants, of anthropological interest perhaps, but not peers or threats or potential partners. The cosmic perspective is essential for maintaining rationality when discussing objects like 3I Atlas. Yes, its behavior is unusual. Yes, it raises questions. But unusual behavior doesn't require extraordinary explanations when the sample size is so small and the phenomena so varied. The universe is complex, governed by physical laws we understand, but with emergent behaviors we're still discovering. Let's shift our perspective from speculation and worst-case scenarios to something more optimistic. The remarkable achievements that the study of 3I Atlas represents, and the reasons for hope that its unusual behavior reveals about the state of human science and cooperation. The very fact that we detected 3I Atlas is extraordinary. A few decades ago, discovering an interstellar object would have been nearly impossible. Our telescopes weren't sensitive enough, our survey programs weren't comprehensive enough, our data analysis capabilities were too limited. The detection of 3I Atlas represents triumph of human ingenuity, international collaboration, and sustained investment in scientific infrastructure. The Atlas survey that discovered this object is a marvel of modern astronomy. It consists of multiple telescopes designed to scan the entire visible sky every night, looking for objects that move, change, or appear suddenly. The system generates massive amounts of data, millions of images, billions of data points, that must be processed rapidly to identify genuine objects of interest amid noise and artifacts. This requires sophisticated software, machine learning algorithms, and human expertise working in concert. That this system works at all is remarkable. That it worked well enough to detect a relatively small, distant object moving at interstellar velocities is a testament to decades of refinement, learning, and improvement. The astronomers and engineers who built Atlas, who maintain it, who develop its algorithms, deserve recognition for creating a tool that has fundamentally expanded our awareness of the cosmic neighborhood. Moreover, the international response to 3I Atlas's discovery has been exemplary. Observatories around the world, professional and amateur, optical and radio, ground-based and space-based, have coordinated to observe this object. Data has been shared openly, analyses have been published and subjected to peer review. This is science working as it should, collaborative, transparent, self-correcting. The renewed activity after perihelion, while puzzling, has been documented carefully. Photometric measurements show brightness changes. Spectroscopic observations characterize the composition of outgassing materials. Orbital calculations have been refined to extraordinary precision. Multiple independent research groups have analyzed the data and published their findings. This process may not yield definitive answers immediately, but it accumulates knowledge systematically. This systematic accumulation of knowledge is profoundly hopeful. It demonstrates that humanity can approach mysteries with rigor and patience. We don't need to jump to unfounded conclusions. We can tolerate ambiguity while working toward better understanding. We can acknowledge what we don't know without filling those gaps with fantasy. The study of interstellar objects also represents practical achievement in international cooperation. Space science requires collaboration across national boundaries. Telescopes are distributed globally to provide continuous coverage as Earth rotates. Data repositories are international. Research teams span continents. Scientists from nations that might have political tensions collaborate effectively because they're united by curiosity and by commitment to discovering truth. This cooperation is a model for how humanity might handle genuinely extraordinary discoveries. If we did detect definitive evidence of extraterrestrial intelligence or artifacts, the framework for international scientific collaboration already exists. The institutional trust, the communication channels, the shared methodologies, all of this infrastructure that enables study of objects like 3I Atlas would scale to handle even more significant discoveries. There's also hope in the public engagement with these stories. You're watching this video. Millions of people around the world follow astronomical discoveries, ask questions, seek to understand. This curiosity is distinctly human and profoundly important. It represents our drive to know, to explore, to understand our place in the universe. That drive has taken us from caves to cities, from superstition to science, from earthbound to spacefaring. The unusual behavior of 3I Atlas serves a valuable purpose even if it ultimately has a mundane explanation. It forces us to refine our models, to question our assumptions, to acknowledge the limits of current understanding. This is how science progresses, not through arrogant certainty but through humble recognition that nature is more complex than our theories predict. Every anomaly is an opportunity. Either we discover it has a conventional explanation and we learn something new about natural processes, or we discover it requires novel explanation and we revolutionize our understanding. Both outcomes represent progress. Both advance human knowledge. The transparency around 3i Atlas is also cause for hope. In an era often characterized by misinformation and conspiracy theories, the astronomical community has shared data openly, acknowledged uncertainties honestly, and resisted sensationalism. Professional astronomers have been clear about what's observed, what's speculated, and what remains unknown. This intellectual honesty builds public trust and demonstrates that science can handle ambiguous data responsibly. Looking forward, the infrastructure we're building will only improve. New telescopes coming online, like the Vera C. Rubin Observatory with its incredible survey capability, will detect many more interstellar objects. Each detection adds data. Each observation refines our understanding. Within decades, we'll have catalogued dozens or hundreds of interstellar visitors, we'll understand their population statistics, we'll be able to distinguish truly unusual behavior from natural variation. This is the trajectory of human progress, from ignorance to knowledge, from fear to understanding, from isolation to connection. The study of 3i Atlas is one small step on that trajectory, but it's a step forward. And that's reason for hope. To fully appreciate the significance of 3i Atlas and the challenge of studying such objects, let's explore the technical details of how interstellar objects are detected and characterized. This is the unglamorous but essential work that transforms cosmic wanderers into scientific subjects. Detection begins with wide-field surveys. Traditional astronomy focused on studying specific objects in detail, particular stars, galaxies, or nebulae. But detecting unknown objects requires a different approach, repeatedly imaging large sections of sky and looking for anything that changes. This is time-domain astronomy, and it has revolutionized our understanding of dynamic cosmic phenomena. The Atlas survey images the entire visible sky every night or two using relatively small telescopes, 0.5-meter apertures, equipped with wide-field cameras. Each image captures a section of sky, and sophisticated software compares new images to reference images from previous nights. Anything that appears, disappears, moves, or brightens gets flagged for further investigation. This sounds simple but involves enormous challenges. The night sky is full of things that change: satellites passing overhead, cosmic rays hitting the detector, asteroids moving through the field, variable stars brightening and dimming, distant supernovae exploding. Distinguishing genuine objects of interest from noise, artifacts, and uninteresting transients requires multiple layers of filtering, automated algorithms followed by human expert review. When 3i Atlas was detected, it appeared as a moving point of light that wasn't in previous images of that region. Its motion was unusual, not matching the pattern expected for near-Earth asteroids or main-belt asteroids. This triggered additional observations to determine its orbit precisely. Orbital determination requires multiple observations over time. By measuring an object's position against the background stars on several different nights, astronomers can calculate its trajectory through the solar system. The mathematics involved, solving equations of motion under gravitational influence, has been refined over centuries since Newton first formulated the laws that govern planetary motion. For 3i Atlas, the orbital calculations quickly revealed something extraordinary. The trajectory was hyperbolic rather than elliptical. This means the object has more than enough velocity to escape the sun's gravity permanently. It came from interstellar space and will return to interstellar space. This hyperbolic trajectory is the definitive signature of interstellar origin. Once identified as interstellar, 3i Atlas became a priority target for detailed study. Larger telescopes were pointed at it to gather more light and enable spectroscopic analysis. Spectroscopy is the technique of splitting light into its component wavelengths, essentially creating a high-resolution rainbow. Different atoms and molecules absorb and emit light at specific wavelengths, creating a unique fingerprint that reveals composition. By analyzing the spectrum of light reflected from 3I Atlas's nucleus and emitted by its outgassing materials, astronomers can determine what the object is made of. Water ice, carbon dioxide, methane, nitrogen, simple organic compounds. Each leaves identifiable spectral signatures. Comparison to spectra from comets in our solar system reveals similarities and differences that hint at the object's formation environment. Photometry, measuring brightness over time, provides additional information. As 3I Atlas rotates, different surface regions reflect different amounts of light depending on their reflectivity and orientation. These brightness variations reveal rotation period and can hint at shape. Changes in overall brightness as the object moves closer to or farther from the Sun reveal outgassing activity and response to solar heating. The renewed activity after perihelion showed up in these photometric measurements. Telescopes monitoring 3I Atlas detected brightening that didn't match the predicted light curve based on distance from the Sun alone. This unexpected brightening triggered the flurry of observations and analyses attempting to understand its cause. Radio observations provide yet another data stream. Radio telescopes can detect emissions from certain molecules in the cometary coma, particularly hydroxyl, OH, and other radicals produced when water molecules are broken apart by solar ultraviolet radiation. These observations confirm outgassing activity and can estimate the rate at which material is being lost from the nucleus. Space-based telescopes contribute observations across wavelengths blocked by Earth's atmosphere. Ultraviolet and infrared observations reveal different aspects of the object's composition and activity. Hubble Space Telescope observations provide extremely sharp images that can reveal structural details impossible to see from ground-based telescopes affected by atmospheric blurring. All of this data gets synthesized into models. Computational simulations attempt to reproduce the observed behavior by adjusting parameters like composition, rotation rate, surface properties, and thermal characteristics. If a model can accurately predict the observations, it suggests we understand the underlying physics. If observations don't match any reasonable model, as with the renewed activity of 3I Atlas, it indicates gaps in our understanding that require either new physics or recognition of scenarios we hadn't considered. The technical sophistication involved in studying interstellar objects represents centuries of cumulative scientific progress. The telescopes, the detectors, the analysis software, the theoretical models, each component builds on decades of prior work. The fact that we can detect objects a few hundred meters across at distances of hundreds of millions of kilometers, determine their composition, track their trajectories with precision, and attempt to understand their behavior represents an extraordinary achievement of human ingenuity. This technical capability also ensures that truly anomalous behavior wouldn't go unnoticed. If 3I Atlas were doing something genuinely inexplicable, emitting radio signals, changing trajectory in ways that violate orbital mechanics, displaying geometric structures, these signatures would be detected and documented. The fact that observations show unusual but potentially explicable behavior rather than wildly anomalous, impossible behavior suggests we're dealing with natural phenomena at the boundaries of our current understanding rather than something fundamentally different. The story of 3I Atlas is far from over. As this object continues its journey outward from our solar system, observations will continue as long as telescopes can detect it. The data gathered will contribute to our growing understanding of interstellar objects and inform our preparations for future discoveries. Several new astronomical facilities coming online in the next few years will dramatically increase our capability to detect and study interstellar visitors. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations soon and revolutionize time-domain astronomy. Its massive 8.4-meter primary mirror and 3.2 gigapixel camera will image the entire visible southern sky every few nights to unprecedented depth. Simulations suggest it might detect dozens or even hundreds of interstellar objects per year once fully operational. This explosion in detections will transform interstellar object science from the study of rare, individual cases to statistical population analysis. With dozens of examples, we'll be able to characterize the typical properties of interstellar objects, their size distribution, composition patterns, trajectory characteristics. We'll learn whether 3I Atlas's unusual behavior is actually unusual or simply represents natural variation we hadn't observed yet due to small sample size. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will conduct infrared surveys that could detect interstellar objects through different observational windows. Its capability to observe in infrared wavelengths will reveal thermal emissions and compositional details difficult to obtain from ground-based observatories. These improved detection capabilities also increase the probability of detecting an interstellar object early enough in its approach to our solar system that an intercept mission might be feasible. Several mission concepts have been proposed for rapid response spacecraft that could be launched to rendezvous with and study an interstellar visitor up close. The European Space Agency's Comet Interceptor mission, approved and currently in development, represents one such concept. It's designed to sit in a gravitational parking spot and wait for a suitable target, either a pristine long-period comet from the Oort cloud or potentially an interstellar object. When a suitable target is identified, the spacecraft would activate and fly to intercept it, deploying multiple probes to study the object from different perspectives. NASA and other agencies have studied similar concepts. The challenge is always timing and propulsion. Interstellar objects move quickly and typically aren't detected until already passing through the inner solar system. Launching a mission requires months or years of preparation. By the time a spacecraft could be ready, the target is usually too far away to reach with conventional propulsion. Solutions might include maintaining standby spacecraft ready for rapid deployment, developing faster propulsion systems, or improving detection capabilities to spot interstellar objects farther out while they're still approaching. Each approach has technical and financial challenges, but the scientific payoff of directly studying an interstellar object would be immense. Looking at broader implications, the study of interstellar objects connects to multiple active research areas. Understanding the composition and properties of objects ejected from other stellar systems informs models of planetary system formation. Every stellar system likely ejects vast quantities of material during its early chaotic phase. Studying the survivors that reach our system tells us about those formation processes. Interstellar objects also serve as potential vehicles for panspermia, the hypothesis that life or its precursors might be transported between stellar systems on natural objects. If organic molecules and even simple life forms can survive the harsh conditions of interstellar space protected within icy objects, then life might not need to originate independently on every inhabited world. It could spread from one system to others, seeding the galaxy with biological material. The search for biosignatures on exoplanets, one of the primary goals of next-generation telescopes like the James Webb Space Telescope, and future extremely large ground-based telescopes, complements interstellar object studies. Both lines of inquiry address the question of life beyond Earth from different angles. Biosignature detection would confirm life exists on other worlds. Interstellar object studies might reveal how life, or its building, blocks spread between worlds. The unusual behavior of 3I Atlas also highlights the need for continued theoretical work in cometary science. Our models of how icy bodies respond to solar heating are clearly incomplete if they can't fully account for the observed activity patterns. Whether the explanation involves exotic volatiles, subsurface structure, rotation effects, or something else, refining these models will improve our understanding of all comets, not just interstellar ones. From a philosophical perspective, every interstellar object reminds us of our cosmic context. We're not isolated. Our solar system is not separate from the galaxy, but embedded within it, exchanging material with the broader galactic environment over cosmic timescales. Objects like 3I Atlas are messengers from that broader environment, carrying information about stellar neighborhoods light years away. As our detection capabilities improve and the catalogue of interstellar objects grows, patterns will emerge. We'll learn whether most interstellar visitors are icy like comets, rocky like asteroids, or show a distribution of properties. We'll learn about their population density in interstellar space. We'll learn whether any show characteristics difficult to explain through natural formation and evolutionary processes.